As a BI professional, you aren't just answering your team's questions. You're empowering them with the data to answer their own questions. By pinpointing the answers they require, you can build tools that enable them to access and use the data they need when they need it. Hey there, welcome to this course. If you've already completed the previous one, you might remember me. But if you're just joining us, I'm Ed. I'm a product manager here at Google. I'm really excited to help you get started with data models and extract, transform, and load, or ETL, pipelines. As you've been learning, BI professionals are responsible for analyzing data to generate meaningful insights and solve problems, answer questions, find patterns, and inform business decisions. A large part of this is building tools to provide stakeholders with ongoing insights. This course is going to focus on those tools and how to automate them in order to pull data from different sources, monitor it, and provide data-driven insights. First, you'll learn about design patterns and database schemas, including common structures that BI professionals use. You'll also be introduced to data pipelines and ETL processes. You've learned that ETL stands for extract, transform, and load. This refers to the process of gathering data from source systems, converting it into a useful format, and bringing it into a data warehouse or other unified destination system. This will be an important part of your job as a BI professional. You will also develop strategies for gathering information from stakeholders in order to help you develop more useful tools and processes for your team. After that, you'll focus on database optimization to reduce response time, or the time it takes for a database to complete a user request. This will include exploring different types of databases and the 5 factors of database performance: workload, throughput, resources, optimization, and contention. Finally, you'll learn about the importance of quality testing your ETL processes, validating your database schema, and verifying business rules. Once you finish this course, you'll apply your skills to a realistic business scenario, which is a great way to demonstrate your BI knowledge to potential employers. As you've been learning, a large part of BI is making other people's jobs easier by automating, simplifying, and enhancing their processes. For example, in one of my projects, I helped the central finance team aggregate years' worth of global sales. This allowed my team to identify the underlying drivers that affected trends in prices and quantities sold. They were then able to clearly report these findings to key stakeholders. I love solving problems and making my team's lives a little easier, which is one of the reasons why I'm so excited to teach you more about data modeling and pipelines in this course. All right, let's get started. Hi, I'm Ed. I'm a product manager at Google. As a product manager, I define the vision for a product and make sure that it aligns with what users actually need that product to do for them. For me, imposter syndrome is a belief that you are not where you need to be in terms of your skill, your perspectives, background, or your experience. I've definitely experienced imposter syndrome. I work with a lot of people who are very, very skilled in their areas of expertise. And not everyone can have every single skill across the board. So you end up thinking, oh, maybe I should be able to, program like her, or maybe I should be as good a data scientist as him, and maybe I should have this level of perspective as it seems like everyone around me does as well. And that's not necessarily true. I really think it's important to focus on the unique perspective that you provide, because everyone's perspective and expertise and interests and the way in which they're going to apply all of those, they're all going to differ. And so there are unique combinations of things that you provide that other people cannot provide simply by virtue of the fact that you are you. I found that the most useful technique in overcoming imposter syndrome is being vulnerable and transparent that you feel that way. Find people that you trust, find people that you can speak with, and tell them how you're feeling. Tell them why you're feeling that way. Feeling a certain way doesn't have to be an indication of who you are or what you're capable of. It simply is. And being able to be vulnerable and say, hey, I don't understand this, or I would like a little bit of extra information, that can be helpful not only for you, but also for people around you. We tend to focus on the negatives. We tend to focus on the challenges or the constructive aspects that we might see that we need to improve on. while not giving ourselves enough credit for the things that we do well, the things that are our strengths that we should lean more into. You're going to be more successful by understanding and really leaning into your strengths than simply trying to hide or run away from your failures. Welcome to the first section of this course. You're going to learn about how BI professionals use data models to help them build database systems, how schemas help professionals understand and organize those systems, and how pipeline processes move data from one part of the system to another. We'll start by exploring data modeling foundations, as well as common schemas and key database elements. We'll also consider how business needs determine the kinds of database systems that a BI professional might implement. We'll then shift to pipelines and ETL processes, which are the tools that move data throughout the system and make sure it's accessible and useful. By the time you're done, you'll have added many more important tools to your BI toolbox. Let's get started. In this video, we're going to explore data modeling, design patterns, and schemas. If you've been working with databases, or if you're coming from the Google Data Analytics certificate, you may be familiar with data modeling as a way to think about organizing data. Maybe you're even already using schemas to understand how databases are designed. As you've learned, a database is a collection of data stored in a computer system. In order to make databases useful, the data has to be organized. This includes both source systems, from which data is ingested and moved, and the destination database, where it will be acted upon. These source systems could include data lakes, which are database systems that store large amounts of raw data in its original format until it's needed. Another type of source system is an online transaction processing, or OLTP database. An OLTP database is one that has been optimized for data processing instead of analysis. One type of destination system is a data mart, which is a subject-oriented database that can be a subset of a larger data warehouse. Another possibility is using an online analytical processing, or OLAP database. This is a tool that has been optimized for analysis in addition to processing and can analyze data from multiple databases. You will learn more about these things later, but for now, just understand that a big part of a BI professional's responsibility is to create the destination database model. Then, you'll organize the systems, tools, and storage accordingly, including designing how the data is organized and stored. These systems all play a part in the tools you'll be building later on, so they're important foundations for key BI processes. When it comes to organization, you likely know that there are two types of data, unstructured and structured. Unstructured data is not organized in any easily identifiable manner. Structured data has been organized in a certain format, such as rows and columns. If you'd like to revisit different data types, take a moment to review this information from the Data Analytics certificate. Now, it can be tricky to understand structure, so this is where data modeling comes in. As you learned previously, a data model is a tool for organizing data elements and how they relate to one another. These are conceptual models that help keep data consistent across a system. This means they give us an idea of how the data is organized in theory. Think back to Furness's perfect train of business intelligence. A data model is like a map of that train system. It helps you navigate the database by giving you directions through the system. Data modeling is a process of creating these tools. In order to create the data model, BI professionals will often use what is referred to as a design pattern. A design pattern is a solution that uses relevant measures and facts to create a model to support business needs. Think of it like a reusable problem-solving template, which may be applied to many different scenarios. You may be more familiar with the output of the design pattern, a database schema. As a refresher, a schema is a way of describing how something, such as data, is organized. You may have encountered schemas before while working with databases. For example, some common schemas you might be familiar with include relational models, star schemas, snowflake schemas, and NoSQL schemas. These different schemas enable us to describe the model being used to organize the data. If the design pattern is the template for the data model, then the schema is the summary of that model. Because BI professionals play such an important role in creating these systems, Understanding data modeling is an essential part of the job. Coming up, you're going to learn more about how design patterns and schemas are used in BI and get a chance to practice data modeling yourself. Bye for now. If you've been working with databases using SQL, you're probably already familiar with relational databases. In this video, you're going to return to the concept of relational databases and learn about a specific kind of relational modeling technique that is used in business intelligence, dimensional modeling. As a refresher, a relational database contains a series of tables that can be connected to form relationships. These relationships are established using primary and foreign keys. Check out this car dealership database. Branch ID is the primary key in the car dealership's table, but it is the foreign key in the product details table. This connects these two tables directly. VIN is the primary key in the product details table and the foreign key in the repair parts table. Notice how these connections actually create relationships between all of these tables. Even the car dealerships and repair parts tables are connected by the product details table. If you took the Google Data Analytics certificate, you learned that a primary key is an identifier in a database that references a column in which each value is unique. For BI, we're going to expand this idea. A primary key is an identifier in a database that references a column or a group of columns in which each row uniquely identifies each record in the table. In this database, we have primary keys in each table: branch ID, VIN, and part ID. A foreign key is a field within a database table that's a primary key in another table. The primary keys from each table also appear as foreign keys in other tables, which builds those connections. Basically, a primary key can be used to impose constraints on the database that ensure data in a specific column is unique by specifically identifying a record in a relational database table. Only one primary key can exist in a table, but a table may have many foreign keys. Okay, now let's move on to dimensional models. A dimensional model is a type of relational model that has been optimized to quickly retrieve data from a data warehouse. Dimensional models can be broken down into facts for measurement and dimensions that add attributes for context. In a dimensional model, a fact is a measurement or metric. For example, a monthly sales number could be a fact, and a dimension is a piece of information that provides more detail and context regarding that fact. It's the who, what, where, when, why, and how. So, if our monthly sales number is the fact, then the dimensions could be information about each sale, including the customer, the store location, and what products were sold. Next, let's consider attributes. If you earned your Google Data Analytics certificate, you learned about attributes in tables. An attribute is a characteristic or a quality of data used to label the table columns. In dimensional models, attributes work kind of the same way. An attribute is a characteristic or a quality used to describe a dimension. So a dimension provides information about a fact, and an attribute provides information about a dimension. Think about a passport. One dimension on your passport is your hair and eye color. If you have brown hair and eyes, brown is the attribute that describes that dimension. Let's use another simple example to clarify things. In our car dealership example, if we explore the customer dimension, we might have attributes such as name, address, and phone number listed for each customer. Now that we've established the facts, dimensions, and attributes, it's time for the dimensional model to use these things to create two types of tables: fact tables and dimension tables. A fact table contains measurements or metrics related to a particular event. This is the primary table that contains the facts and their relationship with the dimensions. Basically, each row in the fact table represents one event. The entire table could aggregate several events, such as sales in a day. A dimension table is where attributes of the dimensions of a fact are stored. These tables are joined to the appropriate fact table using the foreign key. This gives meaning and context to the facts. And that's how tables are connected in a dimensional model. Understanding how dimensional modeling builds connections will help you understand database design as a BI professional. This will also clarify database schemas, which are the output of design patterns. Coming up, we're going to check out different kinds of schemas that result from this type of modeling to understand how these concepts work in practice. In a previous video, we explored how BI professionals use dimensional models. They make it possible to organize data using connected facts, dimensions, and attributes to create a design pattern. A schema is the final output of that pattern. As you've learned, a schema is a way of describing how something, such as data, is organized. In a database, it's the logical definition of the data elements, physical characteristics, and interrelationships that exist within the model. Think of the schema like a blueprint. It doesn't hold data itself, but describes the shape of the data and how it might relate to other tables or models. Any entry in the database is an instance of that schema and will contain all of the properties described in the schema. There are several common schemas that you may encounter in business intelligence, including star, snowflake, and denormalized or NoSQL schemas. Star and snowflake schemas are some of the most common iterations of an actual dimensional model in practice. A star schema is a schema consisting of one fact table that references any number of dimension tables. As its name suggests, this schema is shaped like a star. Notice how each of the dimension tables is connected to the fact table at the center. Star schemas are designed to monitor data instead of analyzing it. In this way, they enable analysts to rapidly process data. Therefore, they are ideal for high-scale information delivery, and they make output more efficient because of the limited number of tables and clear direct relationships. Next, we have snowflake schemas, which tend to be more complicated than star schemas, but the principle is the same. A snowflake schema is an extension of a star schema with additional dimensions and, often, subdimensions. These dimensions and subdimensions break down the schema into even more specific tables, creating a snowflake pattern. Like snowflakes in nature, a snowflake schema and the relationships within it can be complex. Here's an example. Notice how the fact table is still at the center, but now there are subdimension tables connected to the dimension tables, which gives us a more complicated web. Now you have a basic idea of the common schemas you might encounter in BI. Understanding schemas can help you recognize the different ways databases are constructed and how BI professionals influence database functionality. Later on, you're going to have more opportunities to explore these different schemas and even construct some yourself. As we continue our discussion of database modeling and schemas, it's important to understand that there are different facets of databases that a business intelligence professional might need to consider for their organization. This is because the database framework, including how platforms are organized and how data is stored and processed, affects how data is used. Let's start with an example. Think about a grocery store's database systems. They manage daily business processes and analyze and draw insights from data. For example, in addition to enabling users to manage sales, a grocer's database must help decision makers understand what items customers are buying and which promotions are the most effective. In this video, we're going to check out a few examples of database frameworks and learn how they're different from one another. In particular, databases vary based on how the data is processed, organized, and stored. For this reason, it's important to know what type of database your company is using. You will design different data models depending on how data is stored and accessed on that platform. In addition, another key responsibility for BI professionals is to facilitate database migrations, which are often necessary when technology changes and businesses grow. A database migration involves moving data from one source platform to another target database. During a migration, users transition the current database schemas to a new desired state. This could involve adding tables or columns, splitting fields, removing elements, changing data types, or other improvements. The database migration process often requires numerous phases and iterations, as well as lots of testing. These are huge projects for BI teams, and you don't necessarily just want to take the original schema and use it in the new one. So in this video, we'll discuss several types of databases, including OLTP, OLAP, row-based, columnar, distributed, single-homed, separated storage and compute, and combined databases. The first two database technologies we're going to explore, OLTP and OLAP systems, are based on how data is processed. As you've learned, an online transaction processing, or OLTP database, is one that has been optimized for data processing instead of analysis. OLTP databases manage database modification and are operated with traditional database management system software. These systems are designed to effectively store transactions and help ensure consistency. An example of an OLTP database would be an online bookstore. If two people add the same book to their cart, but there's only one copy, then the person who completes the checkout process first will get the book. And the OLTP system ensures that there aren't more copies sold than are in stock. OLTP databases are optimized to read, write, and update single rows of data to ensure that business processes go smoothly, but they aren't necessarily designed to read many rows together. Next, as mentioned previously, OLAP stands for Online Analytical Processing. This is a tool that has been optimized for analysis in addition to processing and can analyze data from multiple databases. OLAP systems pull data from multiple sources at one time to analyze data and provide key business insights. Going back to our online bookstore, an OLAP system could pull data about customer purchases from multiple data warehouses in order to create personalized homepages for customers based on their preferences. OLAP database systems enable organizations to address their analytical needs from a variety of data sources. Depending on the data maturity of the organization, one of your first tasks as a BI professional could be to set up an OLAP system. Many companies have OLTP systems in place to run the business, but they'll rely on you to create a system that can prioritize analyzing data. This is a key first step to drawing insights. Now, moving along to row-based and columnar databases. As the name suggests, row-based databases are organized by rows. Each row in a table is an instance or an entry in the database, and details about that instance are recorded and organized by column. This means that if you wanted the average profit of all sales over the last 5 years from the bookstore database, you would have to pull each row from those years, even if you don't need all of the information contained in those rows. Columnar databases, on the other hand, are databases organized by columns. They are used in data warehouses because they are very useful for analytical queries. Columnar databases process data quickly, only retrieving information from specific columns. In our average profit of all sales example, with a columnar database, you could choose to specifically pull the sales column instead of years' worth of rows. The next databases are focused on storage. Single home databases are databases where all of the data is stored in the same physical location. This is less common for organizations dealing with large data sets and will continue to become rarer as more and more organizations move their data storage to online and cloud providers. Now, distributed databases are a collection of data systems distributed across multiple physical locations. Think about them like telephone books. It's not actually possible to keep all the telephone numbers in the world in one book. It would be enormous. So instead, the phone numbers are broken up by location and across multiple books in order to make them more manageable. Finally, we have more ways of storing and processing data. Combined systems are database systems that store and analyze data in the same place. This is a more traditional setup because it enables users to access all of the data that needs to stay in the system long term, but can become unwieldy as more data is added. Like the name implies, separated storage and computing systems are databases where less relevant data is stored remotely, and the relevant data is stored locally for analysis. This helps the system run analytical queries more efficiently because you interact with relevant data. It also makes it possible to scale storage and computations independently. For example, if you have a lot of data but only a few people are querying it, you don't need as much computing power, which can save resources. There are a lot of aspects of databases that could affect a BI professional's work. Understanding if a system is OLTP or OLAP, relational or columnar, distributed or single-homed, separated storage and computing or combined, or even some combination of these is essential. Coming up, we'll go even more in depth about organizing data. You've been investigating data modeling and database schemas, as well as how different types of databases are used in BI. Now, we're going to explore how these concepts can be used to design data warehouses. But before we get into data warehouse design, let's get a refresher on what a data warehouse actually is. As you probably remember from earlier in this course, a database is a collection of data stored in a computer system. Well, A data warehouse is a specific type of database that consolidates data from multiple source systems for data consistency, accuracy, and efficient access. Data warehouses are used to support data-driven decision-making. Often, these systems are managed by data warehousing specialists, but BI professionals may help design them. When it comes to designing a data warehouse, there are a few important things a BI professional will consider: business needs, the shape and volume of the data, and what model the data warehouse will follow. Business needs are the questions the organization wants to answer or the problems they want to solve. These needs help determine how it will use, store, and organize its data. For example, a hospital storing patient records to monitor health changes has different data requirements than a financial firm analyzing market trends to determine investment strategies. Next, let's explore the shape and volume of data from the source system. Typically, the shape of data refers to the rows and columns of tables within the warehouse and how they are laid out. The volume of data, currently and in the future, also changes how the warehouse is designed, and the model the warehouse will follow includes all of the tools and constraints of the system, such as the database itself and any analysis tools that will be incorporated into the system. Let's return to our bookstore example. To develop its data warehouse, we first need to work with stakeholders to determine their business needs. You'll have an opportunity to learn more about gathering information from stakeholders later. But for now, let's say they tell us that they're interested in measuring store profitability and website traffic in order to evaluate the effectiveness of annual promotions. Now we can look at the shape of the data. Consider the business processes or events that are being captured by tables in this system. Because this is a retail store, the primary business process is sales. We could have a sales table that includes information such as quantity ordered, total base amount, total tax amount, total discounts, and total net amount. These are the facts. As a refresher, a fact is a measurement or metric used in the business process. These facts could be related to a series of dimension tables that provide more context. For instance, store, customer, product, promotion, time, stock, or currency could all be dimensions. The information in these tables gives more context to our fact tables, which record the business processes and events. Notice how this data model is starting to shape up. There are several dimension tables all connected to a fact table at the center. And this means we just created a star schema. With this model, you can answer the specific question, the effectiveness of annual promotions, and also generate a dashboard with other KPIs and drill down reports. In this case, we started with the business's specific needs, looked at the data dimensions we had, and organized them into tables that formed relationships. Those relationships helped us determine that a star schema would be the most useful way to organize this data warehouse. Understanding the logic behind data warehouse design will help you develop effective BI processes and systems. Coming up, you're going to work more with database schemas and learn about how data is pulled into the warehouse from other sources. Earlier, we learned about what considerations go into designing data warehouses. Based on the business needs and the shape of the data in our previous example, we created a dimensional model with a star schema. That process is sometimes called logical data modeling. This involves representing different tables in the physical data model. Decisions have to be made about how a system will implement that model. In this video, we're going to learn more about what a schema needs to have for it to be functional. Later, you will use your database schema to validate incoming data to prevent system errors and ensure that the data is useful. For all of these reasons, it's important to consider the schema early on in any BI project. There are 4 elements a database schema should include: the relevant data, names and data types for each column in each table, consistent formatting across data entries, and unique keys for every database entry and object. As we have already learned, a database schema is a way of describing how data is organized. It doesn't actually contain the data itself, but describes how the data is shaped and the relationships within the database. It needs to include all of the data being described, or else it won't be a very useful guide for users trying to understand how the data is laid out. Let's return to our bookstore database example. We know that our data contains a lot of information about the promotions, customers, products, dates, and sales. If our schema doesn't represent that, then we're missing key information. For instance, it's often necessary for a BI professional to add new information to an existing schema if the current schema can't answer a specific business question. So, if the business wants to know which customer service employee responded the most to requests, we would need to add that information to the data warehouse and update the schema accordingly. The schema also needs to include names and data types for each column in each table within the database. Imagine if you didn't organize your kitchen drawers. It would be really difficult to find anything if all of your utensils were just thrown together. Instead, you probably have a specific place where you keep your spoons, forks, and knives. Columns are like your kitchen drawer organizers. They enable you to know what items go where in order to keep things functional. So your schema needs to include the column names and the data type to indicate what data belongs there. In addition to making sure the schema includes all of the relevant data, names, and data types for each column, it's also important to have consistent formatting across all of the data entries in the database. Every data entry is an instance of the schema. For example, imagine we have two transactional systems that we are combining into one database. One tracks the promotions sent to users, and the other tracks sales to customers. In the source systems, the marketing system that tracks promotions could have a user ID column, while the sales system has customer ID instead. To be consistent, in our warehouse schema, we'll want to use just one of these columns. In the schema for this database, we might have a column in one of our tables for product prices. If this data is stored as string-type data instead of numerical data, it can't be used in calculations, such as adding sales together in a query. Additionally, if any of the data entries have columns that are empty or missing values, this might cause issues. Finally, it's important that there are unique keys for each entry within the database. We covered primary and foreign keys in previous videos. These are what build connections between tables and enable us to combine relevant data from across the entire database. So in summary, in order for a database schema to be useful, it should contain the relevant data from the database, the names and data types for each column in each table, consistent formatting across all of the entries within the database, and unique keys connecting the tables. These four elements will ensure that your schema continues to be useful. Developing your schema is an ongoing process. As your data or business needs change, you can continue to adapt the database schema to address these needs. More to come on that soon. So far, we've been learning a lot about how data is organized and stored within data warehouses, and how schemas describe those systems. Part of your job as a BI professional is to build and maintain a data warehouse, taking into consideration all of these systems that exist and are collecting and creating data points. To help smooth this process, we use data pipelines. As a refresher, a data pipeline is a series of processes that transports data from different sources to their final destination for storage and analysis. This automates the flow of data from sources to targets, while transforming the data to make it useful as soon as it reaches its destination. In other words, data pipelines are used to get data from point A to point B automatically, save time and resources, and make data more accessible and useful. Basically, data pipelines define what, where, and how data is combined. They automate the processes involved in extracting, transforming, combining, validating, and loading data for further analysis and visualization. Effective data pipelines also help eliminate errors and combat system latency. Having to manually move data over and over whenever someone asks for it, or to update a report repeatedly, would be very time-consuming. For example, if a weather station is getting daily information about weather conditions, it would be difficult to manage it manually because of the sheer volume. They need a system that takes in the data and gets it where it needs to go so it can be transformed into insights. One of the most useful things about a data pipeline is that it can pull data from multiple sources, consolidate it, and then migrate it over to its proper destination. These sources could include relational databases, a website application with transactional data, or an external data source. Usually, the pipeline has a push mechanism that enables it to ingest data from multiple sources in near real time or at regular intervals. Once the data has been pulled into the pipeline, it can be loaded to its destination. This could be a data warehouse, data lake, or data mart, which we'll learn more about coming up. Or it could be pulled directly into a BI or analytics application for immediate analysis. Often, while data is being moved from point A to point B, the pipeline is also transforming the data. Transformations include sorting, validation, and verification, making the data easier to analyze. This process is called an ETL system. ETL stands for extract, transform, and load. This is a type of data pipeline that enables data to be gathered from source systems, converted into a useful format, and brought into a data warehouse or other unified destination system. ETL is becoming more and more standard for data pipelines, so we're going to learn more about it later on. Let's say a business analyst has data in one place and needs to move it to another. That's where a data pipeline comes in. But a lot of the time, the structure of the source system isn't ideal for analysis, which is why a BI professional wants to transform that data before it gets to the destination system, and why having set database schemas already designed and ready to receive data is so important. Let's now explore these steps in a little more detail. We can think of a data pipeline functioning in 3 stages: ingesting the raw data, processing and consolidating it into categories, and dumping the data into reporting tables that users can access. These reporting tables are referred to as target tables. Target tables are the predetermined locations where pipeline data is sent in order to be acted on. Processing and transforming data while it is being moved is important because it ensures the data is ready to be used when it arrives. But let's explore this process in action. Say we're working with an online streaming service to create a data pipeline. First, we'll want to consider the end goal of our pipeline. In this example, our stakeholders want to understand their viewer demographics to inform marketing campaigns. This includes information about their viewers' ages and interests, as well as where they are located. Once we've determined what the stakeholders' goal is, we can start thinking about what data we need the pipeline to ingest. In this case, we're going to want demographic data about the customers. Our stakeholders are interested in monthly reports, so we can set up our pipeline to automatically pull in the data we want at monthly intervals. Once the data is ingested, we also want our pipeline to perform some transformations so that it's clean and consistent once it gets delivered to our target tables. Note that these tables would have already been set up within our database to receive the data. And now, we have our customer demographic data and their monthly streaming habits in one table, ready for us to work with. The great thing about data pipelines is that once they're built, they can be scheduled to automatically perform tasks on a regular basis. This means BI team members can focus on drawing business insights from the data, rather than having to repeat this process over and over again. As a BI professional, a big part of your job will involve creating these systems, ensuring that they're running correctly, and updating them whenever business needs change. It's a valuable benefit that your team will really appreciate. We've been learning a lot about data pipelines and how they work. Now we're going to discuss a specific kind of pipeline, ETL. I mentioned previously that ETL enables data to be gathered from source systems, converted into a useful format, and brought into a data warehouse or other unified destination system. Like other pipelines, ETL processes work in stages, and these stages are extract, transform, and load. Let's start with extraction. In this stage, the pipeline accesses source systems and then reads and collects the necessary data from within them. Many organizations store their data in transactional databases, such as OLTP systems, which are great for logging records, or maybe the business uses flat files, for instance HTML or log files. Either way, ETL makes the data useful for analysis by extracting it from its source and moving it into a temporary staging table. Next, we have transformation. The specific transformation activities depend on the structure and format of the destination and the requirement of the business case. But as you've learned, these transformations generally include validating, cleaning, and preparing the data for analysis. This stage is also when the ETL pipeline maps the data types from the sources to the target systems, so that the data fits the destination conventions. Finally, we have the loading stage. This is when data is delivered to its target destination. That could be a data warehouse, a data lake, or an analytics platform that works with direct data feeds. Note that once the data has been delivered, it can exist within multiple locations in multiple formats. For example, there could be a snapshot table that covers a week of data, and a larger archive that has some of the same records. This helps ensure that historical data is maintained within the system while giving stakeholders focused, timely data. And if the business is interested in understanding and comparing average monthly sales, the data would be moved to an OLAP system that has been optimized for analysis queries. ETL processes are a common type of data pipeline that BI professionals often build and interact with. Coming up, you're going to learn more about these systems and how they're created. In previous videos, we've been exploring pipeline processes that ingest data from different sources, transform it to match the destination formatting, and push it to a final destination where users can start drawing business insights. BI professionals play a key role in building and maintaining these processes, and they use a variety of tools to help them get the job done. In this video, we'll learn how BI professionals choose the right tool. As a BI professional, your organization will likely have preferred vendors, which means you'll be given a set of available BI solutions. One of the great things about BI is that different tools have very similar principles behind them and similar utility. This is another example of a transferable skill. In other words, your general understanding can be applied to other solutions, no matter which ones your organization prefers. For instance, the first database management system I learned was Microsoft Access. This experience helped me gain a basic understanding of how to build connections between tables, and that made learning new tools more straightforward later in my career. When I started working with MySQL, I was already able to recognize the underlying principles. Now, it's possible that you'll choose the tools you'll be using. If that's the case, you'll want to consider the KPIs, how your stakeholders want to view the data, and how the data needs to be moved. As you've learned, a KPI is a quantifiable value closely linked to the business strategy, which is used to track progress toward a goal. KPIs let us know whether or not we're succeeding so that we can adjust our processes to better reach objectives. For example, some financial KPIs are gross profit margin, net profit margin, and return on assets. Or some HR KPIs are rate of promotion and employee satisfaction. Understanding your organization's KPIs means you can select tools based on those needs. Next, depending on how your stakeholders want to view the data, there are different tools you can choose. Stakeholders might ask for graphs, static reports, or dashboards. There are a variety of tools, including Google Data Studio, Looker, Microsoft Power BI, and Tableau. Some others are Azure Analysis Service, Cloud SQL, Pentaho, SSAS, and SSRS SQL Server, which all have reporting tools built in. That's a lot of options. You'll get more insights about these different tools later on. After you've thought about how your stakeholders want to view the data, you'll want to consider your back-end tools. This is when you think about how the data needs to be moved. For example, not all BI tools can read data lakes. So if your organization uses data lakes to store data, then you need to make sure you choose a tool that can do that. Some other important considerations when choosing your back-end tools include how to transfer the data, how it should be updated, and how the pipeline combines with other tools in the data transformation process. Each of these points helps you determine must-haves for your toolset, which leads to the best options. Also, it's important to know that you might end up using a combination of tools to create the ideal system. As you've been learning, BI tools have common features, so the skills you learn in these courses can be used no matter which tools you end up working with. Going back to my example, I was able to understand the logic behind transforming and combining tables, whether I was using Microsoft Access or MySQL. This foundation has transferred across the different BI tools I've encountered throughout my career. Coming up, you'll learn more about the solutions that you might work with in the future. You'll also start getting hands-on with some data soon. Recently, you were introduced to data pipelines. You learned that many of the procedures and understandings involved in one pipeline tool can be transferred to other solutions. So in this course, we're going to be using Google Dataflow. But even if you end up working with a different pipeline tool, the skills and steps involved here will be very useful. And using Google Dataflow now will be a great opportunity to practice everything you've learned so far. We'll start by introducing you to Dataflow and going over its basic utilities. Later on, you'll use this tool to complete some basic BI tasks and set up your own pipeline. Google Dataflow is a serverless data processing service that reads data from the source, transforms it, and writes it in the destination location. Dataflow creates pipelines with open source libraries, which you can interact with using different languages, including Python and SQL. Dataflow includes a selection of pre-built templates that you can customize. Or you can use SQL statements to build your own pipelines. The tool also includes security features to help keep your data safe. Okay, let's open Dataflow and explore it together now. First, we'll log in and go to the console. Once the console is open, let's find the Jobs page. If this is your first time using Dataflow, it will say No Jobs to Display. The Jobs page is where we'll find current jobs in our project space. There are options to Create Job from Template or Create Job from SQL. Snapshots save the current state of a streaming pipeline so that you can start a new version without losing the current one. This is great for testing your pipelines, updating them seamlessly for users, and backing up and recovering old versions. The Pipelines section contains a list of the pipelines you have created. Again, if this is your first time using Dataflow, it will display the processes you need to enable before you can start building pipelines. Now is a great time to do that. Just click Fix All to enable the API features and set your location. The Notebooks section enables you to create and save shareable Jupyter notebooks with live code. This is useful for first-time ETL tool users to check out examples and visualize the transformations. Finally, we have the SQL workspace. If you have worked with BigQuery before, such as in the Google Data Analytics certificate, this will be familiar. This is where you write and execute SQL queries while working within Dataflow. And there you go. Now you can log into Google Dataflow and start exploring it on your own. We'll have many more opportunities to work with this tool soon. If you're coming to these courses from the Google Data Analytics certificate, or if you've been working with relational databases, you're probably familiar with the query language SQL. Query languages are specific computer programming languages used to communicate with a database. As a BI professional, you may be expected to use other kinds of programming languages too. That's why, in this video, we'll explore one of the most popular programming languages out there, Python. A programming language is a system of words and symbols used to write instructions that computers follow. There are lots of different programming languages, but Python was specifically developed to enable users to write commands in fewer lines than most other languages. Python is also open source, which means it's freely available and may be modified and shared by the people who use it. There's a large community of Python users who develop tools and libraries to make Python better, which means there are a lot of resources available for BI professionals to tap into. Python is a general-purpose programming language that can be applied to a variety of contexts. In business intelligence, it's used to connect to a database system to read and modify files. It can also be combined with other software tools to develop pipelines. And it can even process big data and perform calculations. There are a few key things you should understand about Python as you begin your programming journey. First, it is primarily object-oriented and interpreted. Let's first understand what it means to be object-oriented. Object-oriented programming languages are modeled around data objects. These objects are chunks of code that capture certain information. Basically, everything in the system is an object. And once data has been captured within the code, it's labeled and defined by the system so that it can be used again later without having to re-enter the data. Because Python has been adopted pretty broadly by the data community, a lot of libraries have been developed to predefine data structures and common operations that you can apply to the objects in your system. This is extremely useful when you need to repeat analysis or even use the same transformations for multiple projects. Not having to re-enter the code from scratch saves time, Note that object-oriented programming languages differ from functional programming languages, which are modeled around functions. While Python is primarily object-oriented, it can also be used as a functional programming language to create and apply functions. Part of the reason Python is so popular is that it's flexible. But for BI, the really valuable thing about Python is its ability to create and save data objects that can then be interacted with via code. Okay, now let's consider the fact that Python is an interpreted language. Interpreted languages are programming languages that use an interpreter, typically another program, to read and execute coded instructions. This is different from a compiled programming language, which compiles coded instructions that are executed directly by the target machine. One of the biggest differences between these two types of programming languages is that the compiled code executed by the machine is almost impossible for humans to read. So, Python's interpreted language is very useful for BI professionals because it enables them to use the language in an interactive way. For example, Python can be used to make notebooks. A notebook is an interactive, editable programming environment for creating data reports. This can be a great way to build dynamic reports for stakeholders. Python is a great tool to have in your BI toolbox. There's even an option to use Python commands in Google Dataflow. Pretty soon, you'll get to check it out for yourself when you start writing Python in your Dataflow workspace. You've already learned quite a bit about the different stakeholders that a BI professional might work with in an organization and how to communicate with them. You've also learned that gathering information from stakeholders at the beginning of a project is an essential step of the process. Now that you understand more about pipelines, let's consider what information you need to gather from stakeholders before building BI processes for them. That way, you'll know exactly what they need and can help make their work as efficient as possible. Part of your job as a BI professional is understanding the current processes in place and how you can integrate BI tools into those existing work streams. Oftentimes in BI, you aren't just trying to answer individual questions every day. You're trying to find out what kinds of questions your team is asking so that you can build them a tool that enables them to get that information themselves. It's rare for people to know exactly what they need and communicate that to you. Instead, they will usually come to you with a list of problems or symptoms, and it's your responsibility to figure out how to help them. Stakeholders who are less familiar with data simply don't know what BI processes are possible. This is why cross-business alignment is so important. You want to create a user-centered design where all of the requirements for the entire team are met. That way, your solutions address everyone's needs at once, streamlining their processes as a group. It can be challenging to figure out what all of your different stakeholders require. One option is to create a presentation and lead a workshop session with the different teams. This can be a great way to support cross-business alignment and determine everyone's needs. It's also very helpful to spend some time observing your stakeholders at work and asking them questions about what they're doing and why. In addition, it's important to establish the metrics and what data the target tables should contain early on with cross-team stakeholders. This should be done before you start building the tools. As you've learned, a metric is a single quantifiable data point that is used to evaluate performance. In BI, the metrics businesses are usually interested in are KPIs that help them assess how successful they are at achieving certain goals. Understanding those goals and how they can be measured is an important first step in building a BI tool. You also know that target tables are the final destination where data is acted on. So, understanding the end goals helps you design the best process. It's important to remember that building BI processes is a collaborative and iterative process. You will continue gathering information from your stakeholders and using what you've learned until you create a system that works for your team. And even then, you might change it as new needs arise. Often, your stakeholders will have identified their questions, but they may not have identified their assumptions or biases about the project yet. This is where a BI professional can offer insights. Collaborating closely with stakeholders ensures that you are keeping their needs in mind as you design the BI tools that will streamline their processes. Understanding their goals, metrics, and final target tables, and communicating across multiple teams will ensure that you make systems that work for everyone. Hey, great work so far. You're almost done with the first section of this course. You've learned a lot. So far, we've discussed a BI professional's role in the organization and storage of data. You also investigated data models and schemas, how BI professionals develop design patterns based on their organization's needs, and how databases are designed. You've been introduced to data pipelines, ETL processes, and building BI tools that help automate moving data from storage systems to target destinations. You've even started using tools to begin building your own pipelines. Finally, you learned strategies for gathering information from stakeholders to ensure that the tools you create for them actually solve the business problems. But creating systems that manage and move data is just one part of a BI professional's job. You also have to make sure that those systems continue working for your stakeholders. Coming up, you're going to discover how to maintain your BI tools and optimize database systems. I hope you're excited to learn more, because there's a lot more I want to share with you. But first, you have another challenge ahead. Feel free to spend some time with the glossary and review any of this section's content before moving on to your next assessment. Then, I'll be here when you're ready to take the next step.
I don't know about you, but when I'm choosing a movie to watch, I sometimes get stuck between a couple of choices. If I'm in the mood for excitement or suspense, I might go for a thriller. But if I need a good laugh, I'll choose a comedy. If I really can't decide between two movies, I might even use some of my data analysis skills to compare and contrast them. Come to think of it, there really needs to be more movies about data analysts. I'd watch that. But since we can't watch a movie about data, at least not yet, we'll do the next best thing. Watch data about movies. We're going to take a look at this spreadsheet with movie data. We know we can compare different movies and movie genres. Turns out you can do the same with data and data formats. Let's use our movie data spreadsheet to understand how that works. We'll start with quantitative and qualitative data. If we check out column A, we'll find titles of the movies. This is qualitative data because it can't be counted, measured, or easily expressed using numbers. Qualitative data is usually listed as a name, category, or description. In our spreadsheet, the movie titles and cast members are qualitative data. Next up is quantitative data, which can be measured or counted and then expressed as a number. This is data with a certain quantity, amount, or range. In our spreadsheet here, the last two columns show the movie's budget and box office revenue. The data in these columns is listed in dollars, which can be counted, so we know that data is quantitative. We can go even deeper into quantitative data and break it down into discrete or continuous data. Let's check out discrete data first. This is data that's counted and has a limited number of values. Going back to our spreadsheet, we'll find each movie's budget and box office returns in columns M and N. These are both examples of discrete data. They can be counted and have a limited number of values. For example, the amount of money a movie makes can only be represented with exactly 2 digits after the decimal to represent cents. There can't be anything between 1 and 2 cents. Continuous data can be measured using a timer, and its value can be shown as a decimal with several places. So let's imagine a movie about data analysts that I'm definitely going to star in someday. You could express that movie's runtime as 110.0356 minutes. You could even add fractional data after the decimal point if you needed to. There's also nominal and ordinal data. Nominal data is a type of qualitative data that's categorized without a set order. In other words, this kind of data doesn't have a sequence. Here's a quick example. Let's say you're collecting data about movies. You ask people if they've watched a given movie. Their responses would be in the form of nominal data. They could respond yes, no, or not sure. These choices don't have a particular order. Ordinal data, on the other hand, is a type of qualitative data with a set order or scale. If you asked a group of people to rank a movie from 1 to 5, some might rank it as a 2, others a 4, and so on. These rankings are in order of how much each person liked the movie. Now let's talk about internal data, which is data that lives within a company's own systems. For example, if a movie studio had compiled all of the data in the spreadsheet using only their own collection methods, then it would be their internal data. The great thing about internal data is that it's usually more reliable and easier to collect. But in this spreadsheet, it's more likely that the movie studio had to use data owned or shared by other studios and sources because it includes movies they didn't make. That means they'd be collecting external data. External data is, you guessed it, data that lives and is generated outside of an organization. External data becomes particularly valuable when your analysis depends on as many sources as possible. A great thing about this data is that it's structured. Structured data is data that's organized in a certain format, such as rows and columns. Spreadsheets and relational databases are two examples of software that can store data in a structured way. You might remember our earlier exploration of structured thinking, which helps you add a framework to a problem so that you can solve it in an organized and logical manner. You can think of structured data in the same way. Having a framework for the data makes the data easily searchable and more analysis ready. As a data analyst, you'll work with a lot of structured data, which will usually be in the form of a table, spreadsheet, or relational database. But sometimes you'll come across unstructured data. This is data that is not organized in any easily identifiable manner. Audio and video files are examples of unstructured data because there's no clear way to identify or organize their content. Unstructured data might have internal structure, but the data doesn't fit neatly in rows and columns like structured data. And there you have it. Hopefully you're now more familiar with data formats and how you might use them in your work. And in just a bit, you'll continue to explore structured data and learn even more about the data you'll use most often as an analyst, coming soon to a screen near you. Databases are essential tools for data analysts. I use them constantly. Just about all of the data I access is stored within databases. Databases store and organize data, making it much easier for data analysts to manage and access information. They help us get insights faster, make data-driven decisions, and solve problems. You've already heard a bit about what databases are and how they're used by data analysts. Now let's learn more about database features and components. Here's a simple database structure. It contains tables with information from a car manufacturer. The top level includes car dealerships, product details, and repair parts. Then, if you drill down to the next level by selecting one of those tables, you'll find more specific details about each item. This is called a relational database. A relational database is a database that contains a series of related tables that can be connected via their relationships. For two tables to have a relationship, one or more of the same fields must exist inside both tables. For example, here, branch ID exists in this table and this one. If a field exists within both tables, we can use it to connect the tables together. The branch ID field is the key to connecting these tables. There are two types of keys. A primary key is an identifier that references a column in which each value is unique. You can think of it as the unique identifier for each row in a table. For our dealership table with information about the different dealership branches, branch ID is the primary key. Similarly, for the product details table about each car, VIN is our primary key. As an analyst, you may need to create tables. If you do decide to include a primary key, it should be unique, meaning no two rows can have the same primary key. Also, it cannot be null or blank. There are also foreign keys. A foreign key is a field within a table that's a primary key in another table. In other words, a foreign key is how one table can be connected to another. Because our repair parts table contains information about each car part, the primary key is part ID. Each row in our repair parts table represents one unique part. All the other keys in this table, such as the VIN, are the foreign keys that allow the repair parts table to be connected to the other tables. As you can see, a table can only have one primary key, but it can have multiple foreign keys. Understanding primary and foreign keys can be tricky, so you'll have more opportunities to practice coming up. But as a general summary, a primary key is used to ensure data in a specific column is unique. It uniquely identifies a record in a relational database table. Only one primary key is allowed in a table, and they cannot contain null or blank values. And a foreign key is a column or group of columns in a relational database table that provides a link between the data in two tables. It refers to the field in a table that's the primary key of another table. Lastly, it's important to note that more than one foreign key is allowed to exist in a table. Feel free to rewatch this video to be sure you understand primary and foreign keys clearly. And coming up, you'll begin practicing how to access and analyze data from actual databases. That will be a great opportunity to improve your understanding of primary and foreign keys, database organization, and how you might use databases in your future analytics career. Hey there! In this video, we're going to learn about each part of the BigQuery SQL workspace so you can use it during this course and throughout your career as a data analyst. It's an extremely valuable and widely popular tool, so understanding how it works is super helpful. Feel free to follow along on your screen as we explore BigQuery. You may notice that my screen appears a little different than yours, since BigQuery is constantly updating its interface. Don't worry if this happens, as minor differences won't stop you from understanding the basics. To begin, go to the BigQuery landing page. Then, log into the account you created earlier. To navigate to the SQL workspace, select the menu on the left side of the screen and scroll down to the Big Data header. Then, hover over the BigQuery label and click SQL Workspace from the dropdown. Now that we're in the SQL workspace, we're going to search for public datasets, select a dataset through the Data Explorer, run a query, and upload our own data for querying. First, we'll search for a public dataset to use. To select a public dataset, navigate to the Explorer menu on the left side of the screen. Click the Add Data button in the upper right of the menu. Then, in the drop-down menu, select Explore Public Datasets. This will open the Marketplace and show you available public datasets. Let's go to the Search Marketplace bar and search for NOAA_Lightning, a dataset we'll use in an upcoming activity. Click on the Cloud to Ground Lightning Strikes dataset. This will give us a description and preview of the dataset, which captures observations about lightning activity and weather patterns in the United States. Click View Dataset. This will bring you back to the SQL workspace and create a tab for the dataset. We can then move back to the Editor tab we have open, or click Compose New Query to begin writing with SQL. On the left, notice that the BigQuery Public Data drop-down list is in the Explorer menu. We can click the arrow to expand the BigQuery data list and pick out a new dataset. Let's select the first dataset in the drop-down list, Austin_311. When we do, it expands to show the table within the dataset. We can open the dataset for a preview. The Schema tab contains the names of each column in the dataset. The Details tab contains additional metadata, such as the creation date of the dataset. The Preview tab contains the first rows from the dataset. On this page, we can click Query to automatically create a new editor window with the template for a query already populated. From here, put an asterisk after Select, where our cursor pops up. Then, run the query. Congratulations, you ran a SQL query in BigQuery. The query you ran returned rows from the dataset, which populate in a window beneath the editor interface. Results from any query you run will also display here. Now let's say you have the results of a survey that you want to upload to BigQuery and analyze using SQL. To add your own data to BigQuery, choose the ID of the project you want to add to. Select the 3 vertical dots icon to open options for the project, then choose Create Dataset. Name the dataset something that will help you identify it later, such as Upload Test Dataset. Then click Create Dataset. Next, go to the Explorer menu and choose the 3 vertical dots next to the dataset under the project's dropdown. Now, we'll select the icon for Create Table, which opens a pop-up window. Under Source and Create Table From, select Upload or whichever method you prefer to upload your data. Here, we can upload any data file, such as a CSV file. Let's give our table a helpful name, such as test_table. Make sure that the schema is set to auto-detect and select Create Table. There's more to come with BigQuery. Feel free to rewatch this video anytime and keep practicing. See you soon. Hey there! In this video, we're going to learn about each part of the BigQuery SQL workspace so you can use it during this course and throughout your career as a data analyst. It's an extremely valuable and widely popular tool, so understanding how it works is super helpful. Feel free to follow along on your screen as we explore BigQuery. You may notice that my screen appears a little different than yours, since BigQuery is constantly updating its interface. Don't worry if this happens, as minor differences won't stop you from understanding the basics. To begin, go to the BigQuery landing page. Then, log into the account you created earlier. To navigate to the SQL workspace, select the menu on the left side of the screen and scroll down to the Big Data header. Then, hover over the BigQuery label and click SQL Workspace from the dropdown. Now that we're in the SQL Workspace, we're going to search for public datasets, select a dataset through the Data Explorer, run a query, and upload our own data for querying. First, we'll search for a public dataset to use. To select a public dataset, navigate to the Explorer menu on the left side of the screen. Click the Add Data button in the upper right of the menu. Then, in the drop-down menu, select Explore Public Datasets. This will open the Marketplace and show you available public datasets. Let's go to the Search Marketplace bar and search for NOAA_Lightning, a dataset we'll use in an upcoming activity. Click on the Cloud to Ground Lightning Strikes dataset. This will give us a description and preview of the dataset, which captures observations about lightning activity and weather patterns in the United States. Click View Dataset. This will bring you back to the SQL workspace and create a tab for the dataset. We can then move back to the Editor tab we have open, or click Compose New Query to begin writing with SQL. On the left, notice that the BigQuery Public Data drop-down list is in the Explorer menu. We can click the arrow to expand the BigQuery data list and pick out a new dataset. Let's select the first dataset in the drop-down list, Austin_311. When we do, it expands to show the table within the dataset. We can open the dataset for a preview. The Schema tab contains the names of each column in the dataset. The Details tab contains additional metadata, such as the creation date of the dataset. The Preview tab contains the first rows from the dataset. On this page, we can click Query to automatically create a new editor window with the template for a query already populated. From here, put an asterisk after Select, where our cursor pops up. Then, run the query. Congratulations, you ran a SQL query in BigQuery. The query you ran returned rows from the dataset, which populate in a window beneath the editor interface. Results from any query you run will also display here. Now let's say you have the results of a survey that you want to upload to BigQuery and analyze using SQL. To add your own data to BigQuery, choose the ID of the project you want to add to. Select the 3 vertical dots icon to open options for the project, then choose Create Dataset. Name the dataset something that will help you identify it later, such as Upload Test Dataset. Then click Create Dataset. Next, go to the Explorer menu and choose the 3 vertical dots next to the dataset under the project's dropdown. Now, we'll select the icon for Create Table, which opens a pop-up window. Under Source and Create Table From, select Upload or whichever method you prefer to upload your data. Here, we can upload any data file, such as a CSV file. Let's give our table a helpful name, such as test_table. Make sure that the schema is set to auto-detect and select Create Table. There's more to come with BigQuery. Feel free to rewatch this video anytime and keep practicing. See you soon.